Fellow computer graphics enthusiasts, when it comes to any interactive application or video games, collision plays an important role in deriving physics for any virtual object.
What the f?
In Houdini there are several genius methods that already takes care of this. But, as usual, let's reverse engineer this. The aim of this video is to walk you through the basic principles of collision detection and response behaviors. What you see on your screen was totally done using Vex and solvers from scratch. And after watching this video, you'll be able to try it for yourself. Let's begin. So the first thing that we'll understand is, how can we compute if a point in space is inside or outside of a closed mesh? Step 1. Cast a ray from point P to the closest point on the collision mesh, and call it point I. The ray Pi will be stored as a vector r. Step 2. On point I, store the surface normal, n, of the collision mesh. Step 3. Compute a dot product between vector r, surface normal, n, of the collision mesh. Step 4. If dot product is positive, greater than 0, then the point P is outside the given collision mesh. If dot product is negative, less than 0, then the point P is inside the given collision mesh. This is how we can compute if a point in space is inside or outside a collision mesh. Let's implement the same in Houdini. Let's make a point, a collision mesh, make sure to add correct normal. Let's add this mesh in the second input for the point wrangle. Here's the code. We can see how the color of the point changes from green to red as soon as it goes inside the collision mesh. Let's now understand the concept of overlapping between two particles having a certain radius. The aim of this section is to compute if a point P and point Q with radius r1 and r2 respectively are overlapping or not. Step 1. Compute the distance between point P and point Q and call it dist. Step 2. Compute the sum of two radius, r1, and r2, call it SR. Step 3. Compute the difference between the sum of two radius, SR, and distance, dist. Step 4. If difference is positive, greater than 0, then the overlap is true. If difference is negative, less than 0, then the overlap is false. This is what the implementation in Houdini looks like. I have 2 points with different radius, in this case, P scales. And as soon as one of the point touches the other, you can see how the indicator changes from away to in proximity, and even overlapping. You can see the code and try it yourself. Remember these 2 lines that I have commented for now, we'll use them later. Let's take the previous theory and take it one step ahead. The aim for this section is to compute a directional vector for both points and offset position of points by half the overlap amount. This will resolve the overlap and relax the position of each point. Step 1. Compute the directional vector PQ and QP, and normalize them. Step 2. Offset the position P and Q by half the amount of overlap in the direction of normalized PQ and QP, respectively. Let's implement the same in Houdini. Remember the 2 lines of code I had commented out? This is doing exactly what we just described. Calculating the axis and offsetting the position by half the overlap amount. Let's uncomment them. And there you go, this is a simple version of how we can do point relaxation. All that needs to be done is to make this work for multiple points, not just one. And it's very simple to do. We just have to iterate the code in a way that each point checks for intersection exactly the amount of the number of points available to iterate on, and put all of that blunder into a loop. In our case, a for loop. Here's how I did it. You can see as I increase the iterations, the points are relaxing till all the overlaps are resolved. Alright. Now we've learned and prepared enough wrangles to start working on our own collision solver. Let's start with the free-falling solver we prepared in our last video, which was about spring mass system, and use that as a starting point. If you have not watched that video, I'll recommend checking it out. I'll wait. Let's grab the setup and modify it so we have multiple point emission. Inside the solver, let's merge the previous frame to every fourth frame. Here I have added some variations in p-scale and velocities. Also, let's add a collision sphere as a second input. Make sure it has correct normals for collision. In my case, I have reversed the normal as I want to trap the particles inside. Right now we only see some emission and nothing is colliding. Let's take the ray casting wrangle and add it inside the solver. Don't forget to add the collision to the second input. Let's modify the wrangle so that the velocities are reversed every time an intersection is detected. This step is what we call a collision response or behavior. We need to calculate an axis of collision, then we swap the vector components parallel to the collision axis. Let's also multiply a damping value for each collision. A very important side note, this method that we're using to generate response and behavior also takes conservation of momentum, friction, air resistance, temperature, and many more principles into account. These values result in a much more accurate damp values. In our case we're keeping things simple, by using a random damping value, but feel free, if you want to calculate those values, and multiply them. Let's also correct the sphere instance size before we do anything. Let's play and check. Okay, we see a problem already. First, the particles are colliding with the collision mesh, and that's okay, but the particles aren't colliding among each other. To solve this, we can simply take our point relaxation wrangle, along with the for loop, and just place it before we're calculating any intersections. This will ensure that particles are always resolving their overlap. In this case, we don't need much iterations as we're already giving it enough substeps. Let's play and check. Great. We can see the particles are not intersecting among each other now. But we have one more problem now, that is, the particles are now escaping the collision mesh. This is happening due to the relaxation push happening between subframes. To solve this, I have added a simple wrangle, to always push the particles in the container, as they're escaping. This wrangle may look very similar to point relaxation, but do not be confused, it's just a fail-safe. Let's play and check. Amazing! We have everything working correctly now. And if we disable the gravity, and play, we see something similar to the preview videos I showed in the beginning. While this is okay, what about the collision behavior among the particles themselves? We can see the particles are bouncing back when they're being collided with an external collider, but they're not doing so among each other. Let's solve this. We just simply add the response behavior code that we used in the ray casting wrangle. Let's also enable the gravity again. Let's play and check. And there we go. We did it. We have made our own collision solver. Now we can use it in any way possible. I tried using it on my spring mass system setup and the results didn't disappoint. Alright. I hope I was able to demonstrate something useful. You can further read about momentum conservations and other principles for collision detection. What we did just now was only scratching the surface. There are many optimization principles that I couldn't demonstrate as they'd make much more sense to be shown in OpenGL. If that's something you want, then let me know in comments. Till then, I am out.